All right, we are going to be starting chapter 3 in this section on quadratic functions. And I will tell you that there is quite a bit going on in this section, so you really want to make sure that you focus on learning these aspects. So, quadratic functions, if you recall, are those ones that have a power of 2. It was deceitful with the name of quad, but projectiles in the real world can be modeled by a quadratic function or quadratic functions. A quadratic function is any function of the form f of x equals ax squared plus bx plus c. One of these equations can determine the height of a projectile at any time t. This section we will work more with these quadratic functions whose graphs are referred to as parabolas. And so we've seen some of those with transformations, and so we are going to check them out again. Now, the leading coefficient of the highest power of 2, which is a, actually, we call it a up there in that formula right there. It is important in determining the orientation of the parabola. Now, all these parabolas that we look at today are going to be going up and down in a sense in this section. So if a is greater than 0, if it is positive, what we will have is a parabola that is kind of pointing upwards. It has a vertex down here, which is actually going to be a minimum point, it's the farthest down that we have. And we have something that is referred to as the axis of symmetry. We've known that with parabolas that we do have that symmetry, and so here is our axis of symmetry with that. If a is less than 0, then what happens is that I have a parabola that's turned upside down, kind of like a mountain. What we have up here is our vertex still, but now it is a maximum point because that's the farthest up that I can go with that. And we also still have that axis of symmetry. So there are parabolas that will go side to side, that will go kind of left and right, one to the right and one to the left, but we will not get into that with these at this point. Okay? All right, now, the vertex that I've talked about, let's flip to the next page. The vertex is the turnaround point of a parabola. The vertical line that goes through the vertex and divides the parabola into half is what we call the axis of symmetry. Undo that. And the equation of this graph with a quadratic function will always be x equaling h, where h is the x-coordinate of the vertex. And we'll get into that in just a second when we apply some of this with our problem. So, standard form, just like what we talked about in section 2.8 with standard form of a circle, we have a standard form for a quadratic function as well. So I'm going to write it as this for our function notation. If I have a times an x minus h squared plus k, where a is not equal to 0 is in standard form. Now, the graph of our function f is a parabola whose vertex point is h comma k. Now notice back up here that h is grouped with that x, so I have to take the opposite of what I'm looking at here, but I take this sign as is. The parabola is symmetric with respect to the line x equaling h, which is our axis of symmetry. Okay, lots of ways to put it here. Now, knowing the parent graph of a function f of x equals x squared is so important. So, we're going to review this in a t-chart sense. So, if I look here, if I do a t-chart, and I plug all these values into this function and I square them, I get all of these. So when I graph my original parent graph of my parabola, remember we're over 2 and up 4, and then we have our matching points over here because of our axis of symmetry. that goes through our vertex. So this is the parent graph of all of our quadratics. Now, what I want you to remember are these points here, because this is what's going to navigate us to our other points whenever we start moving things from side to side. So, all right, so this means from my vertex, I would move over 1 and up 1. From my vertex, move over 2 and up 4. So you can see that from here. This vertex, move over 1 and up 1, over 2 and up 4. That's going to be very helpful whenever we are graphing these other ones that have moved, okay? Now, if the function is in standard form, what was standard form? We just saw it up there. That is that a times x minus h squared plus k. You don't have to write that, but I just want to rewrite it again for you so you see it since it's off the screen. The vertex is easy to find. You must take the opposite of what you are looking at with the x and take the sign as is of the number at the end to find the vertex labeled as hk. Okay? One can also find the x and the y intercepts. Now, remember how to find the x-intercepts. We got to let y equal 0, because it was kind of opposites, if you remember that from chapter 2. And when we're finding the y-intercept, we have to let x equal 0, and these are going to be special points that we can use in order to kind of guide and help with our graph, okay? So we're going to kind of put all of that together here in a couple examples to show you how we can do that when it's in standard form. So notice here I have my standard form. I have a times x minus h quantity squared plus k. Okay? Now notice there's no number in front. It is an invisible 1. It is positive. So since a is greater than 0, then it opens which direction? Well, that's on our page over here on the back side that we just started with. If a is positive, it opens up in the positive direction is the way I remember that. If a is negative, it's pointing towards the negative direction is the way I remember that. Okay? So, a is less than 0. So here a equals 1, I should say. And it's going to open up. I'm going to identify the axis or the vertex first before I go on to the axis of symmetry. If I look at the opposite of what I'm looking at, take this sign as is. So therefore the vertex is 2, 1. Now, from that vertex, this 2 is very important because that is always going to drive the axis of symmetry. Axis of symmetry is always x equal to some number, and that number has to be the h value of your vertex, or the x value of your vertex. So x equaling 2, this line, x equals 2, is a vertical line at x equaling 2. That's where we're going to mirror around. Now, the domain of any parabola, this is what for ones that go up and down, I will tell you is always going to be all reals. So we're, by interval notation, going to go from negative infinity to positive infinity, okay? But the range is going to be determined about whether or not that graph goes up and down and from the vertex, okay? So I'm going to go ahead and graph this vertex. I'm going to go over 2 and up 1. Now, this a value does not change the original t-chart. If you remember those common points that I just told you to remember, this is our guide to doing our graph. So we are going to go from our vertex. Remember, that's our vertex. Here's our new vertex. This tells me to go over 1 and up 1, over 2 and up 4. So over 1 and up 1 gives me this point since it's going up. Over 2, 1, 2 and up 4, 1, 2, 3, 4 gives me this point. And so that's half of my parabola, but because of my axis of symmetry, now I can mirror image those other points on the other side, therefore giving me that graph for my parabola, which is going to be helpful with finding the range. So I come from negative infinity all the way up, and I start with a value here at y equaling 1 to infinity. So that's going to help me get my range. And then, to find the x and y intercepts, we need to let y equal 0, we need to let x equal 0. But, if we notice from our graph, this is a nice one that we don't even have to actually plug numbers in to solve. If I look for my x-intercept, where does that parabola cross the x-axis? That is nowhere. Therefore, there is no x-intercept or none for x-intercepts. Now, on my y-intercept, notice here, I can see where it crosses. It's actually going to cross at 5, so therefore my y-intercept is going to be at 5. So, how do you find that? Find y-intercept algebraically. We're going to let x equal 0, so in here, my y is equal to 0 minus 2 squared plus 1. This gives me 4 plus 1 definitely is the 5. So you can use the formula all day long or the equation all day long to determine those, but you do not have to, okay, in all of the sense. All right, very good. That was one. Again, standard form, a equaling 1. Here we have a standard form where a is going to be different than 1. Here's my a times my x minus h squared plus k. So the a this time is negative 2. So therefore, a is less than 0. And since that's the case, my parabola is going to open down. Now, let's identify my h and my k. Take the opposite, take as is. So opposite of negative 1 is positive 1. Take this sign as is negative 4. So I'm going to, whoops. Let's go ahead and make this, in order for us to fit on our graph let's make that a positive 4. So take that sign as is. So let's graph that point at 1, 4. That's going to be my vertex. Now, once you have your vertex, let's talk about the axis of symmetry. It's always x equal to the x value of your vertex. So it's x equaling 1. And if I graph that line, that's what it would be. Domain is always going to be all real numbers for all of these parabolas. But our range is going to be dependent upon where that we graph it. Now, when a equals negative 2, that means that from my original points that I have here of 0, 0, 1, 1, 2, 4, that means that all of these y values have to be now multiplied by negative 2. So I'm going to end up multiplying by negative 2. That gives me a 0, a negative 2, and a negative 8. Now, what does that mean in relation to my graph? That means now I need to go from the vertex of 0, 0. I'm going to go over 1 and down 2. Instead of going over 1 and up 1, now I'm going over 1 and down 2. That gives me this point. I'm also then from the vertex going to go over 2 and down 8 because I can now multiply by that a. 1, 2, 3, 4, 5, 6, 7, 8 would be right here. And what I now can do with my axis of symmetry is match those points on the other side. And that's what we have. So here's one side of my parabola, and there's the other side of my parabola. So there's the graph of that. So what we can do now is it's going to be very, very helpful for us to end up looking at my range from this. And that's going to be from negative infinity, all these values, until I max out at positive 4. So this is going to be from negative infinity to 4. Okay. All right. Now, do we have any x-intercepts? Oh, most definitely we have x-intercepts, but this time they're not very nice. Do I have a y-intercept? Yes, I have a y-intercept right there at 2. So I could go ahead and put that down by my graph. Again, I can let x equal 0. But here's the case when I have to find my x-intercepts, and I need to set the y value equal to 0. So basically I need to do negative 2, x minus 1 squared plus 4, set that equal to 0, and now we need to solve that. Now there's multiple ways to solve this, but the easiest way is to get this quantity squared by itself, square root both sides, and solve for x. Now you can square it all out, do the quadratic formula on it if you want, but I think the easiest way is to isolate this expression. So I'm first going to subtract 4, and I get negative 2 times x minus 1 squared equals a negative 4. Then to get this expression by itself, I'm going to now divide by 2, all of that by 2, and actually a negative 2. Which means I divide that side by negative 2, so this goes away, leaving me with x minus 1 squared equals, this here becomes a positive 2. Now what I want to do is to square root both sides. to get into that x. So I need to square root this side, square root that side. Do not forget the plus or minus on that right side. Again, we've done that multiple times, so you want to make sure that you have that. And you have x minus 1 on the left. This becomes plus or minus root 2 on the right. And to solve it all the way down for x, I need to add 1 to both sides. And therefore, 1 plus or minus root 2 is going to be the exact version of my x-intercepts. So sometimes you might have to use some other way in order to solve that equation in order to get it together. So please make sure that you watch that. Okay? All right, let's try a couple more of these, and then we've got one more idea with some max and mins. And unfortunately, I lost my graph over here, okay? So we'll just make one up. Make up our coordinate grid. Okay, so here I have a function, x squared plus 1. Hopefully you recognize there's nothing grouped with the x, and then I have that plus 1 at the end. So this is actually of the form, yes, a times x minus h squared plus k. Just that when I don't have anything grouped with the x, remember that is a 0. Take the sign as is, therefore my vertex is going to be 0, 1. Now look at what the a value is. It's a 1 in front. So a is greater than 0, therefore the parabola opens up. Axis of symmetry. Now that I have my vertex, it's going to be at x equaling 0. My domain is going to be always all real numbers for these guys. Now let's graph so we can get the rest of it. So I'm going to graph my vertex at 0, 1. Then I'm going to use the idea that my a is equal to 1. Therefore, I can use those values for the original. From the vertex, we go over 1 and up 1. Over 1 and up 1 gives me that guy. And then over 2, 1, 2, and up 4. 1, 2, 3, 4. Gives me that guy right there. Axis of symmetry is at x equaling 0. Therefore, I have a point over here and a point approximately there that's going to create my parabola. Okay? So this is the point 2, 1, 2, 3, 4, 5. So this is at 2, 5. This is at 1, 2. This is at negative 1, 2. And this is at negative 2, 5. Okay? So since I don't have a grid there. Now, what do we know about the range? If I come up negative infinity, there's nothing until I start at 1, y equaling 1, to infinity. Therefore, that is going to be my range. Are there any x-intercepts along that x-axis? The answer is no. And do I have any y-intercepts along the y-axis? And the answer is yes, right there at y equaling 1. So here on this one, the advantage is I don't really have to do very much algebraically to find my x and y-intercepts because I can see them on my graph. Okay? All right, let's look at this last one in standard form, and then we'll move on to talk some max and mins. So this is a little bit different of a form that we see. I like to go ahead and kind of bring this plus 1 at the end and write this as negative x minus 3 squared plus 1 to keep it in that form of a times x minus h squared plus k. Okay, so a here is a negative 1. A equals negative 1. Therefore, it's less than 0, which would mean it opens down. Take the opposite of what you're looking at inside with the x. Take this sign as is. Therefore, this is going to be at 3, 1 for my vertex. The axis of symmetry is always x equaling the x-axis or the x-coordinate of your vertex, which is 3. The domain is always going to be negative infinity to positive infinity. So now let's go ahead and graph 3, 1. That gives me this guy. And of my values, 0, 0, 1, 1, 2, 4, a here is negative 1. So that's what you want to multiply all of these by to get the new values that I need in order to locate those points. Now, once you know this is your vertex, again, you can throw 4 and 5 into the original equation and figure out what kicks out for the y value, but I think this pattern work is so much easier than to have to plug and chug all those numbers. So because of our pattern work with our a, our original points from our vertex, we're going to go over to the right and down 1. we're going to go over 2 and down 4, negative 4. 1, 2, 3, 4. So it's all in relation to that vertex. Here is my axis of symmetry. So that means that a mirror image, this is going to be a point, and this is going to be a point, and this gives me my parabola. Okay? All right, so let's do our range next. Let's do from negative infinity, and I maxed out at y equaling 1. So we're going to go from negative infinity to 1 and include that. And then let's talk about x-intercepts. Can I find them easily on my graph? Yes, we can. It's here and here. That's at 2 and 4 are going to be our x-intercepts. But unfortunately, my y-intercept doesn't come into play on my graph. So this is again where we have to go back to find a y-intercept. We're going to let x equal 0. You can also let y equal 0 in that equation and find it if it's not obvious on your graph. So let's throw 0 in for x here. Y is equal to the opposite of 0 minus 3 squared plus 1. This gives me a negative 3. Squared is 9, so I have a negative 9 here plus 1, which gives me negative 8. Therefore, my y-intercept is at negative 8. So it's down here somewhere that it's going to cross. Okay? So here are 4 examples of the types of things you're going to have to work with quadratic functions, and you want to make sure that you're capable of doing that within these types of problems. So here's the big kind of characteristics of some of these things that we're going to kind of work with. If I give you a function that is not in standard form, okay? So now what if the function is not in standard form and is given as f of x equaling ax squared plus bx plus c? It can be proven by completing the square that the x-coordinate of the vertex is given by x equals negative b over 2a. X equals negative b over 2a. Now, once you know what that number is, to find the y-coordinate, we're simply going to plug that x-coordinate back into the original function to find the complete xy point for that. Now, we can also discuss maximum and minimums of the function. So if a is greater than 0, recall we had a parabola that went like this, then the graph has a bottom out point there. It has a minimum at x equaling negative b over 2a, and y is going to come from plugging that negative b over 2a into my function. Now, if a is less than 0, that means I have a parabola that went upside down pointing towards the negatives, and that means I have a maxed out point at the top. I have a maximum at x equaling negative b over 2a, and its y value is also going to be found by plugging that negative b over 2a into our function. Okay, so I know that looks like a lot, but remember that x equaling negative b over 2a is very, very important. Now, the domain of a quadratic function, we've said it 4 times in the problems above, is always going to be all real numbers. The range is determined by the y value, which in turn will determine if the graph goes up or down. Now, if the graph opens up, which is like this, remember, then there is a minimum whose range will be that I want all y values greater than or equal to that minimum. Now, if the graph opens down, then remember there is a maximum, and the range will be everything less than or equal to that max. So we want y to be less than or equal to the maximum. Okay? So here we get a function that is in standard, or not standard form, it's in general form, what they call it. And we need to determine all these same things with this graph, okay? So we're going to use the vertex and the intercepts to graph each quadratic function, then give the axis of symmetry, domain, and range. Okay, so notice here I have ax squared plus bx plus c. A here is equal to -1. Therefore, a is less than 0. This graph is going to open down. The vertex is at -b over 2a. So we have ax squared plus bx plus c. So a equals -1, b equals +4, and c here is equal to 1. So you always take the sign that is in front of each one of those. Now, what is -b over 2a? If I take the opposite of b, which is -4, over 2 times a, which is -1, I get -4 over -2, which is 2. That means that the x value of the vertex is equal to 2. Now, to find the matching y value, I need to plug that into the original function. So y is going to come from taking -2 squared plus 4 times 2 plus 1. Wherever I see an x in this function, I've got to plug 2 in. So I get y equals, this is -4 plus 8 plus 1, which gives me a 5. Therefore, 2, 5 is the vertex of this function. Now, once I have the vertex, I can get my axis of symmetry because it's x equal to this number. X equals 2. The domain is always all real numbers. And we need to now determine if we have a, let's see, let's go ahead and graph it. Let's do that first. Let's go over 2 and up 5. That gives me that point. Now remember, what is our little pattern here for our points that we need to plot? Here's our original. But remember, a is -1. So if I multiply everybody by -1, that gives me my new places that I need to go. So over 1 from the vertex and down 1. Over 2 from the vertex and down 4. 1, 2, 3, 4. Gives me these points right here. Here is my axis of symmetry. Then I have a mirror image over here of this and a mirror image of this point right here. Now that point's actually very nice because I'm crossing the y-axis there. Hence, that is my y-intercept of 1. How can I also get that? That's by putting x equaling to 0 into the original function. So I get -0 squared plus 4 times 0 plus 1, which is also, I put an extra parenthesis there, this gives me that, okay? So make sure you can work it out either way, from the graph or from the equation. Now, let's go to our range, because we have -infinity. All those values will occur until I get to my maximum. That's where I have the range to be y is less than or equal to my maximum. So interval notation leads me to write -infinity until I get to the y value of 5 here, and including 5. Okay, now the last bit of information is that we have to figure out what these x-intercepts are. And fortunately, they're not very nice. So I'm going to take this equation, and we're going to let y equal 0. So we're going to replace that f of x term with 0. So I get -x squared plus 4x plus 1, set that equal to 0. I'm going to extend my page up a little bit. Now, this is something that I have, we could factor it possibly. First off, I want to get rid of that negative. So I'm going to divide everybody by -1, just so that I end up getting my positive x squared that I like to see. And when I divide by -1, basically I just change the sign. Now the question is, can I factor it? Is there anything that I can multiply to get 1 that I subtract to get 4? And unfortunately, the answer to that is no, nada. So I'm going to use the quadratic formula to find out what this is. So you got to remember what the quadratic formula is. So it's x equal to -b, so positive 4, plus or minus the square root of b squared, which is 16, minus 4 times a times c, all over 2a. If you have to sing it, please do so. So x equals -b plus or minus the square root of b squared minus 4ac all over 2a. So what do we get? I'm going to simplify this. This is 16. This becomes a -4. So 16 minus a -4, that becomes a +4 in here. So that actually is the square root of 20 all over 2. And this goes back to working with radicals. What is the perfect square in 20? Well, square root of 20 can be broken as the square root of 4 times the square root of 5. So when I square root that +4 in the front, that gives me a 2 square roots of 5. So this becomes 4 plus or minus 2 square roots of 5 all over 2. And because I have a 2 in all spots, bam, 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 right there, that means I can cancel a 2 with all of them. So cancel a 2, and cancel a 2 with everything on the outside. Final answer becomes 2 plus or minus root 5 all over 1, but I'm not going to write the all over 1. That would be our answer. So 2 plus or minus root 5. And this is where it kind of all comes together and the culmination of that. Okay, so that is if you don't have standard form to begin with. That's a little bit more difficult, so you got to make sure you know how each piece works. Okay? All right, and our last one is dealing with those minimum and maximums that I had in that last box. Knowing which way the graph goes, we're not going to get as involved in these, but we are going to be able to determine where the maximum and the minimum occur, okay? So, for each equation, we're going to determine without graphing whether the function has a minimum value or a maximum value, and that is determined by A. Find the minimum or maximum value and determine where it occurs. Identify the function's domain and range. Well, we can easily put in the domain right now because we know if it is a function that the domain of any parabola or quadratic function has to be all real numbers. So that's done, okay? Now, for f of x, we are determining A. A is the x squared term. A here is 2, which means that A is positive, which means I end up having a parabola that goes like that. So if I have a parabola that's pointing up, that means I have a bottom out point that is my minimum. So we know that. So the minimum value is going to be the k value when an x value occurs at my vertex. So the x value of the vertex goes for my axis of symmetry. The y value is very, very helpful in determining the max or the min, okay? Now, where is that minimum going to occur? Well, the minimum occurs at negative b over 2a for the x value. I have to determine this first, and then I'm going to plug it into my function to determine the y value of my vertex. So b here in this case is negative 8, so I need the opposite of negative 8 all over 2a, which is 2. So this becomes an 8 over 4, which is 2. So if I added a piece here just for my vertex, we have 2 is the x value, but what is the y value? I now need to determine the y value from my function. Put in 2 for an x. Square it, multiply by 2, then I'm going to subtract 8 times 2 and then subtract 3. So this becomes 2 squared, which is 4, times 2 is 8, minus 16 minus 3. And if I do that, I end up with negative 11. So the vertex for this parabola is at 2, negative 11. That negative 11 is important because that is the max or the minimum value. So in this case, we have a minimum at negative 11 when x equals 2. There's the h, there's the k. There's the h, there's the k. So if I end up having a parabola that goes up like this, and negative 11 is my minimum, that's going to play a part in my range. Negative 11 to positive infinity is what my range is going to be because all those values have to be greater than or equal to that minimum value. So you don't even have to graph it fully, specifically, but a nice idea of that graph is going to be helpful here. Okay. Now this function, the last one we have here, kind of is moved around a little bit. So I'm going to write this as negative x squared minus 4x plus 5 so that we can see our ax squared plus our bx plus our c. So in this case, a is negative 1, b is negative 4, and c is 5. Now, if a is -1, that means that a is less than 0. That means I end up having a parabola that looks like that. It is a mountain. We have a maximum value at wherever that vertex is right there. Now, we need to find the vertex by doing our -b over 2a. So do the opposite of -b all over 2 times a. Top becomes a +4, bottom is a -2, therefore the vertex x value is -2. Let's now use that within my function to determine the y value. Y comes from taking the opposite of the -2 squared minus 4 times -2 plus 5. And again, I just put -2 right in here and right in here. So, what do we get? -2 squared is 4, but I have opposite of that, so a -4. This becomes a +8 when I do -4 times a -2, and then I have a +5. So -4 plus 8 is 4, plus 5 is a 9, and therefore that is the y value of my vertex. That is exactly where the maximum occurs at -2, 9, when x equals -2. The domain is here, and if I have a parabola that goes like this, that means that I'm coming up from -infinity, and I'm maxing out here when y equals 9. There's my vertex at -2, 9. So I have to go from -infinity to +9 as my range. Okay, so I know that's a little bit involved. I know that has a lot of pieces to that, but I've tried to separate it out for you to be able to go back and look over these problems and kind of work with the problems that you're going to practice on in order to master this concept. Okay, so until next time.